All right. Well, welcome, cohort. Gosh, I'm losing track now. I guess you're cohort A. No, cohort B. Cohort B. I'm sorry. Cohort B. The one I saw today. This is your lesson for tomorrow. I'm actually recording it the night before, so it's a little confusing. All right. So, guys, the story so far. Okay, we've been talking about graphing, and the story so far, just to put it in a nutshell for you. Okay, goes like this. Sorry, I'm just fiddling with my computer at home here. Yeah, if you have a position time graph, you know that if you take the slope, I'm just going to go like this, it gives you the velocity. Now, if you have a velocity time graph, and you take the slope of that, it gives you the acceleration. Okay, so velocity is the rate of change in position. And so when we take slope, we find the rate of change in something. So when we have the position time graph, if you take the slope of this, you get velocity. Now, if you take the slope of the velocity time graph, once you have a velocity time graph, you take the slope of that, you'll get the acceleration. Now, we also found that the area under a velocity time graph is equal to the change in position. So it's equal to delta D. Okay? And here's the thing, what we're going to learn today is that the same thing applies with the acceleration time graph. If you had acceleration time graph here, what you're going to find is that if you take the area underneath that one, that's equal to, but not the change in position this time, but the change in velocity. So I just want you to see if you can see this pattern here, okay? So we start with a position time graph. If you were to measure the slopes all over that graph, you would generate a velocity time graph, okay? Now, if you were to take the slopes on the velocity time graph, you would generate an acceleration time graph, okay? Now, going backwards, if you take the area underneath the acceleration time graph, that gives you the change in velocity, so it tells you what the change in velocity is. And by the same token, if you take the area under a velocity time graph, that tells you the change in position, okay? So slopes move you this way, okay? From position to velocity to acceleration, and area underneath moves you that way, okay? So slope moves, you know, to the right, and area moves you, okay? So this is area equals delta D, and here, area equals delta V, okay? So anyway, I just wanted to point that out to you as kind of an interesting way of thinking of it, if you like. It's a little bit of a summary. And that brings us to the first topic for today's lesson, which is acceleration time graph. So I included this here, and it's an explanation on how acceleration time graphs work. Okay, so we know that the value on the line, so if you're just reading this out to you, the value on the line, of course, is the acceleration, right? So it's, after all, it's an acceleration time graph. So if you're reading off the value, that's going to equal the acceleration. Now the change in acceleration, you just a2 minus a1, delta a, you know, makes sense. Now here's an interesting thing. Okay, the slope of the acceleration is actually equal to a quantity. I'm not making this up. It's called jerk, okay? So when something accelerates, its velocity is changing. Well, if the acceleration changes, the rate of change in acceleration is something called the jerk. So that's what the jerk is equal to, is the slope on a acceleration time graph. Now, actually, we're not going to, you can keep going, you know, you keep taking the slope and then finding something else. So we could draw a jerk versus time graph. The slope of that would be equal to something called snap, okay? The slope on a snap graph would equal crackle. Okay, and this, I'm not making this up, and the slope on a crackle graph would equal pop. okay? But we're never going to go there, okay? So we're going to stop here at the acceleration time graph, and really that's enough, okay? Like I never did anything. We never looked at jerk in university even, okay? And you don't need it, okay? It's really not necessary. So anyway, slope of tangent, of course, would be the instantaneous jerk. So there's something interesting, okay? Because like, you know, tangent line, that's how it is, right? So anyway, here's the deal. To summarize all of this, really it's all about the area under the line. So the area under the line is equal to the change in velocity on an acceleration time graph. So it'll tell us what the change in velocity is. It can't tell us what the initial velocity is, but it can tell us what the changes in velocity are, okay? And just like on the acceleration on the velocity time graph, if the line is above the axis, then the area would be below the line. Okay, whoops. No, okay, so yeah. And if it says here, if the acceleration is negative and the line is below the axis, the area above the line would equal a negative change in velocity. Just like on a velocity time graph, if it's below the line, it's a negative change in position or negative displacement. Okay, so anyway, that's it. So what do acceleration time graphs look like? Well, here's an example. This one is kind of complicated. So it's not a uniform acceleration. We can see the object's rate of acceleration is increasing over time. And then what happens is the rate of acceleration varies in its curved path here. But the area, whether it's curved or straight, doesn't matter, the area underneath, okay? Yeah, I don't like how this is worded. Let me change this. The area beneath the curve between at any time interval is the change in velocity. Okay, so let me cross out these words because it just doesn't make sense. Okay, and that's it. Now, what about slopes? Don't worry, we're not going to be looking at the slope on this graph. So we're done. We're done. This is the last graph we're going to look at. All right, now I have an example of an acceleration time graph for you here. These look kind of unusual, but let me tell you how you interpret it. Okay, so if you look at it, there's some questions here at the bottom. So what is the acceleration of the object during the first 2 seconds? Well, here we can see that the seconds, I'll just zoom in a little. There's 1, 2, 3, 4, and 5. So during the first 2 seconds, the acceleration is holding constant rate here at, like right here, okay, that line, and that's at 15 meters per second squared. So acceleration is measured in meters per second squared, right? At the 7-second mark, the acceleration is negative 10 meters per second squared down there. So these tick marks represent 5 meters per second squared intervals. At 20 seconds, you would have to read it right here. So that looks like it's 5 meters per second squared at 20 seconds. So you get the idea, okay? Now, it's the next question. I'm going to erase these markings that I made because it'll get too messy otherwise. All right, so now the next question, it says, what is the change in velocity for the whole trip? Well, like I told you, the change in velocity is the area. I'll shade in the areas. You always have to go from the line to the axis when you're measuring these areas. So here we can see these areas down here. Sorry, my highlight is a little thick, so it's hard to go, hard not to stay inside the lines. But anyway, now you just have to find the areas of these boxes. Now you divide it up into convenient shapes. So I'll make a triangle at that last little spot there. So, this is area number 1. It'll be 5 times 15, right? Area number 2 here, this is, 10. It'd be negative 10 actually. Negative 10 times here's 5 seconds from here to here. So negative 10 times 5. Area 2 is equal to that much. Okay, area 3 here would equal, again, it's 5 seconds, and the height is 10 actually. So it would be 5 times 10 again, except this time a positive 5 times positive 10. And finally, the area of this triangle here, area number 4, would equal, the base of the triangle is 10 units long from here to here. So it'd be 10, and the height is 10 units high times 10 divided by 2. Okay, using the formula for the triangle, you know, half the base times the height, okay, or base times height divided by 2. So anyway, all of this, if you add it all up, the change in velocity will equal the total area. Okay, will equal the total area, which is equal to area 1 plus area 2 plus area 3 plus area 4, right? And that's how you find the change in velocity on a acceleration time graph. Okay, so that's how you'd answer a question like letter B. Now, it says here, what is the average acceleration for the whole trip? Well, the definition of average acceleration is just the change in velocity divided by time. Okay, so all you have to do is get the total area and divide by time. Okay, and that's it. Now, jerk is slope. So that one is slope. So just measure the slope. Slope of tangent, you would just read off, like we talked about this today, so I'm going to let you try that. During which, this is easy, during where, how can you tell if the acceleration is 0, positive, and negative? Well, the value on the line itself tells you the acceleration. So let me just circle in red for you. Here, anywhere where the acceleration, like here, the acceleration is 15, well, that's positive. Here it's positive, and here it's positive. So in those 3 areas, it's positive. The only place where it's negative, and I'll use a blue color, right there is where the acceleration is negative, right? And that, well, actually this whole box here, that's where it's negative, where it passes below 0. Okay, so acceleration is just the value on the line. So it's plus 15, it's minus 10, you know, and so on, depending on which area it's in here. Where's the acceleration 0? Well, the acceleration is 0, I'll use a rainbow color. Oops. The acceleration is 0, I'm going to circle the spots with the rainbow. That's what I meant to do anyway. There, and there, where the line touches 0, right? So that's it. Yeah. So, guys, that's how you determine where the acceleration is 0, positive, and negative. Now, it says here to sketch the corresponding position time graph. I'm going to cross that one out. I'm not going to ask you to do that one. That is a difficult question to do. And actually, you know, if you're curious, I can show you how to do it. Never going to come up though. So let's, you know, it's pandemic time. We got to go fast. Let's skip the questions that I'm never going to ask you anyway. Okay. That's kind of a tedious question too. So we're going to cross that one off the list. So anyway, that's how you do acceleration time graphs. And, you know, no problem, right? Now, just to, so that you want to get a little summary of everything we've been talking about. Oh, that's really small. Okay, so here I have a little chart. See if you could fill this in from memory. So this should say not displacement, but position. Position and displacement are the same thing if you start at position 0. Okay, so that's why sometimes we use the word displacement. Anyway, on a position time graph, what's the position mean? Well, what's the y-intercept mean? Now, y-intercept is where the line touches the y-axis. Now, the y-axis on a position time graph is position, actually. Okay, and the y-intercept would represent the initial position. Okay, and of course, on a velocity time graph, it would represent the initial velocity. Okay, and here the initial. See, the y-intercept happens when x is 0, but here we have when time is 0. Well, that's the initial condition, right? I'm going to let you fill these things in. Here, slope, just to give you a sense of it though, I'll just say it. Slope on a position time graph represents velocity, right? So slope of tangent would be instantaneous velocity. A positive slope would mean a positive velocity. A negative slope would mean a negative velocity. And a 0 slope would mean a 0 velocity, right? But on a velocity time graph, a positive slope would mean, sorry, slope of tangent would be the instantaneous acceleration. A positive slope would be a positive acceleration. Negative slope is a negative acceleration. And a 0 slope would be 0 acceleration, and so on. Okay, and on acceleration time graph, the slope means jerk. And so you can just put in instantaneous jerk, positive jerk, negative jerk, so on, okay? Try to fill this in, okay? Try to fill all of this in. What is the meaning of all this? Now, in case you're getting stuck, there's a little secret for you. Underneath are the answers here. Oops, look at that. But I would really like you to try to do it first, like try to think of what it means. Because remember, your goal here is not simply to copy information that someone else gives you. It's to try to understand it, okay? And remember what slope of tangent means, you know, how we interpret straight lines and curved lines on these graphs. Remember, a straight line on a position time graph just means it's a uniform velocity, and a curved line means it's a changing velocity or non-uniform velocity. Okay, in other words, the slope is changing on a curved line, and slope is velocity, right? All right, some of them have no meaning, like this one here, area under a position time graph has no meaning, so you can leave that one blank, okay? All right then, so now the answers are here, just in case you want to get them from there. I just wanted to point that out to you. Now, I'm almost done the lesson. There's one more thing I would like you to do, and since you're at home, I would like you to try this on your own, and I'd like to show you. I have a worksheet for you here. It's called the Moving Man worksheet. Now, you have seen me use this applet in class. Okay, you saw me use it today. So now, the Moving Man. The Moving Man is the applet where the man is moving back and forth. I'm not sure if I showed you that today. I think I did. Anyway, I get confused between my two physics classes because I had another physics class this morning. Okay, so anyway, see this website here? Okay, here's how you find the Moving Man on the web. Just go to a browser, okay? Go here, and I'm gonna type in, I'm not gonna write it, I'm gonna type it, because that's a pain. So I'm just gonna type PhET, like that, Moving Man. Just Google that, okay? The first link that comes up, click on it. Okay, and then press play on the simulation, and it'll take a moment to initialize the simulation. So we'll just wait here a moment. Okay, graphics is initializing, that's wonderful. Then you see this Moving Man starting up. Beautiful, there it is. Okay, so there's our Moving Man. Now, if you read the instructions on the sheet I gave you, we'll come back to that applet in a moment. It says here, after the Moving Man is open, leave the position time graph. So here, I'll just highlight this for you. Leave the position time graph and the velocity time graph open, but close the acceleration time graph by clicking on the symbol in the upper right corner of the graph. Let me show you how to do that. Okay, so go to the Moving Man, and I actually want you to do this, guys. Okay, so like I want you to do it. It's like a little virtual lab. You have to, what it doesn't tell you is you have to click on charts. So click on charts, right? And now that we've clicked on charts, what we're gonna do is we see the three graphs. It says to close the acceleration time graph. So you see right over here where my mouse is moving around, that's the acceleration time graph. I'm gonna click on the symbol and now it's closed. All right. Now we'll return to our instructions. It says, investigate the Moving Man by dragging the dude around with your mouse. This will give you very jumpy data, especially acceleration graph, but we're not looking at the acceleration graph anyway. Now it says why. You don't have to answer that question, but like it's because you're randomly moving it around with your hand, right? Now try making the man move using the slider arrows. Use the playback features to look at the graphs. So, pardon me, getting a little tired. So let me show you that. Okay, so there's two ways for me to move the man. I can grab him and move him around, and the video will probably look quite choppy. Okay, here I am moving it kind of slowly. Okay, position versus velocity time graph. Now he's moving the positive direction. Right, it's like that. Okay, and then I can pause this. I can zoom in on the graph. Okay, I can zoom out on the graph. I can even slide this around. So like, see this is another way to move the man around. I can do that. And I can do this to make him move with various velocities. So if I press play here, now I've got him moving a certain velocity. Well, I can change that velocity by just sliding my little, guy back and forward. So here I can set the velocity. I can even set his position. Okay, so here I am setting his position by dragging the arrow. So I just want you to play with it. And we can see it's a very chaotic looking line. All right, so far so good. Now, what I'd like you to do next is just follow the instructions. So it says for each of the 6 scenarios below, predict what the velocity and time graph will look like. A velocity and position time graph will look like. Don't be afraid to be wrong. Okay, so let's look at this. A man moving from the center of the screen to the house at a slow, steady pace. So that means he's going to, here's my prediction. Okay, I'll do the first one with you. So he starts, whoops, I don't want that. He starts at 0, okay? So it starts at 0, and he moves to the house, which is at positive 8 meters at a slow, steady pace. So that's gonna look like that, okay, where he stops at around the 8 meter mark. Now, what does the velocity time graph look like? Well, it's a slow and steady pace. So steady means it's a uniform velocity. So a uniform velocity, I think, and I'm really good at this, will look like a horizontal line. Now, I'm only sketching it, okay? You can do a better job, maybe with a ruler or something, and draw 2 straight lines there. One of them, of course, is diagonal because he's moving, changing position. The other one, though, is just a horizontal line. And what you can do is you can now check, okay, with the moving man himself and see if you were right about this. So let's clear all this. Now it says here he starts at 0. So actually I'm going to move him to position 0. And I'm going to reset the thing. Actually, I'll enter position 0. It's probably simpler. There, he's at 0. I'm going to pause it. Okay, and I'm going to clear it. Now, here's the deal. He's going to move to position 8 at a slow and steady pace. So what I'm going to do is I'm going to give him a small velocity. Let's make it, I don't know, 2 meters per second would be a nice and slow, steady pace, I guess. Let's make it 2. Actually, I'll just type the number in. 2. There you go. Now, I'm going to press play. There he is going at a slow and steady pace. Okay. And then I'll make him stop at the house right there. So look at that. Now, was I right? Okay, did I make the right prediction? Well, I go back to my sheet here. I said that the position time graph would look like a diagonal line, okay, going from 0 to 8. Does it do that? Yes, it does. That's the blue line here at the top. Now, I said that the velocity time graph would be a horizontal line at some number between 0 and 5 because it's a slow pace. So I look at it, and that's what I have, okay? So, it says here, explain your reasoning for the appearance of the graphs. Well, a uniform velocity, they both should be straight. You know, you can explain it. To be honest with you, let's cut out the explain questions. That's just annoying. I just want to see that you can do it. Okay, I don't really care if you can explain it. I hope you could explain it to your own self so that you can do this. Okay. Now, if we use a faster pace, what about that? Okay, how will that look different from the graphs above? A man standing still at the 4 meter mark, what would that look like? Oh, pardon me. All right, so now what you're going to do is you're going to keep doing this, okay, and see how it all works out. And then what you do is you keep going back to the app and testing it. So look at this, a man moving from 0 to the house at a fast pace, then moving back to 0 at a slower pace, okay? So if you want to see how you would do letter D, go back to the moving man, clear everything, okay? I reset everything, so I reset all the settings. He goes back to the middle. I'm going to close this acceleration time graph again. So it says from 0 to the house and back to 0 again. All right, so what I'm going to do is I'm going to set a velocity, okay, of 3 meters per second, let's say. I'm going to press play. Okay, so when he gets to the house, I'm going to press pause. Pause it there. Now to get back to the starting point, I'm going to change his velocity to -3. So now he's going to turn around. Okay, now I press play again. And back he comes, back to 0. And when he gets to 0, I will press pause right there. All right. So take a look, okay, at the position time graph and the velocity time graph. Can you predict that? Okay. All right. So, guys, for today and for today's homework, what I'd like you to do is I'd like you to do the Moving Man worksheet. So go through this, see if you can, how well you can guess what it is, okay? And then in this graph here, just explain what the man is doing. Okay, it's a position time graph. What is he doing? Like break it up into little sections. Like you can make it, section A, section B here, section C. What's he doing in each section? Just describe it in words. Okay. And then there's one last question here at the end. It says now using the values of X, V, and A in the boxes, what you want to do is you have a goal. Okay. You want him to, you want him to get to the wall. Okay. He starts at one wall. Start at the left wall, move all the way over, okay, to the right one, turn around and come back without hitting the right wall. Okay. Now, can you set 3 values in those boxes that will make him do that by itself? Okay. Like, in other words, you don't want to turn him around like I did and enter, you have to have one set of values, X, V, and A. Okay. And that's it. So give it a try, see if you can do it. Pardon me for all the yawning. Gosh, it's been a long day. All right, guys, so that's it for now. If you look at the homework outline, all right, so what have we done? So now what we've done is we have completed this part here, and we're kind of reviewing now. Okay, so that's lesson 5. We're not going to look just yet at this. We're going to spend a little more time on graphing. So please do not do lesson 6 just yet. Okay, homework. Please do not do that. Do instead, okay, the Moving Man activity and the worksheet I gave you. So no new textbook homework today. Okay, so I'd just like you to do that. I'm keeping it light for today. So sometimes it'll be a little heavy, sometimes it'll be a little lighter. We're going to stop there for today. And guys, like that's it for graphing. We're going to move on after this. So we'll do a little review. We'll have a quiz. Okay, and what we've learned so far about average velocity, average speed, vectors, scalars, and graphing, of course, and see if you're understanding things so far. Okay, and then we're going to move on in the meantime, okay, before we have that quiz. So for cohort A, the quiz will be on Friday. For cohort B, the quiz will be on Monday. All right, so guys, have a good day, and we will see you tomorrow.